Welcome everyone to the SIMBa seminar. Today we have Sergio García as our speaker. He's now visiting the University of Barcelona, and now he's doing his PhD in the Universitat Autónoma of Madrid. And his talk will be about an introduction to Khovanov homology and annular. So,
thank you very much for the introduction and inviting me to this seminar. I'm very glad to be here and talk about a bit about Khovanov homology and knot theory. You can interrupt me anytime and ask any questions. And well, this is a joint work with both my supervisors. Okay, so this will be a bit of the contents we are going to see. First, we'll start with an introduction of some definitions of knot theory, like what is a knot, for example. Then we'll introduce the Jones polynomial, a very important invariant. And lastly, we'll see the Khovanov homology. There's a fourth section right here, but I promise there won't be any slides about it. It's just kind of a space for me to talk about what we are currently working on. And also along all these sections, we'll introduce both the classical knots and its annular counterparts. Okay, so first of all, what is a knot? A knot is just a set of points in R3 or S3 that is homeomorphic to S1. So we have something like this. And if we take a disjoint union of knots, we get a link. On the right side of the image, we have a diagram that is just a projection of our knot into the plane. But we can ask ourselves why limit ourselves to R3 or S3. Maybe we can consider knots in other three manifolds. One of these manifolds can be the thickened annulus, which is A times I, where A is the annulus, which is S1 times I. Okay. And you can consider knots in other three manifolds or other thickened surfaces. Okay. And an annular link is a disjoint union of annular links. Okay. Here we have the thickened annulus, and we have a knot and a diagram that represents it. We will represent annular diagrams in a plane with a point removed. Okay, so we will be in R2 minus the origin. Okay. So then we need also a notion of equivalence between knots. And we'll say that two knots are equivalent if there is an ambient isotropy that transforms one knot into another. Okay, it's this thing right here. And if we change R3 for the thickened annulus, we get the notion of equivalence of annular links. And we say that two diagrams are equivalent if the knots they represent are equivalent. And an invariant is just a function that whose value only depends on the type of knot. Okay, so if you have two equivalent knots, then the value is the same. This value can be a group, can be an integer, a polynomial, whatever. And this is a very important theorem. It's one of the classical results, which tell us that we can actually work with diagrams and forget a bit about the knots. Okay, so we don't have to work in R3, but we can just work on the plane. And two diagrams are equivalent if we have a sequence of movements that transform one diagram into another. Okay, and we see that these movements kind of make sense, right? Because if we have something like a string in R3 and we have something that looks like this, okay, like a loop. So in R3, we can just untwist it, and we see that this should be an equivalent knot. And this is what this Reidemeister move tell us in R2. This same theorem exists for the annular links. We just need to be a bit careful that right here we have the point we have removed, the puncture. So there are some moves that are not legal. Okay, so as long as the point we have removed is far away from the movement, there's no problem. Okay, like in the first row, everything there is allowed. The second row is not. Also, we can orientate any node by just giving one of the two orientations there are. And if we do this for every component of the link, we have an oriented link. And associated to each crossing, we have a sign plus or minus, okay, following the following rule. If we approach the crossing by the underpass, okay, so the one that's split in two, if the overpass goes from left to right, that's a positive crossing, and otherwise we say it's a negative crossing. And the number of positive crossings minus the number of negative crossings, we call it right of a diagram. Okay, we'll see why it's important. Now we introduce the Jones polynomial. This is one of the most important invariants there are, and one of the most studied ones. Thanks to this polynomial, Jones earned the Fields Medal, so it's kind of important. And we will define it using the Kauffman bracket. Okay, so the Kauffman bracket is just a polynomial that satisfies these three axioms. The first axiom tells us that the unknown has Kauffman bracket 1. The second one allows us to remove one circle that's like disjoint from the rest of the diagram just by multiplying for this term. And the third one is what we call skein relation. And this skein relation relates three diagrams that are exactly the same, except in a small neighborhood that they differ as the pictures show. Okay, so you can imagine that this is part of a huge diagram, maybe with a lot of crossings, whatever. But locally, it looks like this. The crossing looks like this, and you can change it for this one and compute the Kauffman bracket. So applying this axiom, you can reduce the number of crossings. So you'll get to 0 crossings. So you'll have only circles, and then you can eliminate them using both the first and second axiom. This is not exactly a link invariant, but if we just multiply it by this thing right here, we get a link invariant, and this is the Jones polynomial. We have also a definition for annular links, which is exactly the same, but we get two more axioms, because right now, when we get two circles in the plane, we have two types of circles. Ones that bound this in the plane, like this, and ones that don't. So these are what we call trivial circles, and these are essential circles or non-trivial circles. And it appears this new variable h, which kind of measures how many times the node winds around this central pole. Okay, remember that we are in an annular in a thickened annulus. Okay, so we kind of have like this central pole. And same as before, we multiply by this factor and we get the annular Jones polynomial. And we have a cool property that if our node is inside here, but it kind of is inside a ball, so you have your node on something like this. So it's kind of far away from this ball. Then we see that it should behave as if it was a regular node, and indeed, that's what happens. So that's something good to have. But we will actually use another definition of the Jones polynomial. Okay, this is another polynomial that we call bracket polynomial. if you see the left side of the equations are exactly the same, so it's exactly the same maximum, but we just change a little bit the coefficients on the right side. Okay. Just know that this is another polynomial. It's not an invariant, but if you multiply by some things right here, you get the same Jones polynomial, just in another variable. Maybe you have to do a change of variables, but it's exactly the same. Why we use this? Because we want to define something called the Kauffman state, which is just an assignment of a label 0 or 1 to each crossing. So to each crossing, we label it 0 or 1. And this is a smoothing. Okay, so we kind of eliminate the crossing by smoothing it. And if we change the crossing for the thing we have on the left, that's what we call a zero smoothing. And a zero smoothing if we change it for the thing on the right. So to each, for example, if we have here the trefoil knot, we can assign a label 0 to the first crossing, a label 1 to the second crossing, and a label 0 again to the third one. And we can smooth those crossings as the label tells us. So we change this crossing by something that looks like this crossing by something that looks like this, and the third one by something that looks like this. And we get a new diagram that is what we will call also the Kauffman state 0, 1, 1. Okay, and why is this useful? Well, it's important to note that when we talk about annular links, we will have both trivial and essential circles. For example, this smoothing right here, which is a one smoothing, produces an essential circle and a trivial one. And why is this important? Because we can actually define the Jones polynomial, or to be precise, we define the last polynomial we saw in terms of the Kauffman states. Okay, so we have a closed formula that only depends on the Kauffman state. So we have this sum over all Kauffman states of something, some q's, and this sum of q's that only depends on the state x. Okay, R is basically the number of ones that we have. So in this right here, R would be 1 because we only have 1, 1. And K is the number of circles we have. So right here we have 2 circles, so K could be 2. And this allows us to compute the Jones polynomial in an easy way. We said that it only depends on the Kauffman states. So we put all Kauffman states, but we arrange them in a special way, making this kind of cube. Okay, if you see, this is just a cube on some perspective, but it is a cube. And we just arrange them by the number of ones they have. So in this 0 column, we put all the states that have 0 ones. So there's only 1. On this first column, we put the states that have 1, 1. So 1, 0, 0, 0, 1, 0, 0, 0, 1, and so on. And then we put, we decorate each vertex by the polynomial that comes with that state. And if you see, it just corresponds to a copy of Q for the number of ones they have. So here it's Q to the 0, here appears 1 Q, here 2 Qs, and 3 Qs. And a copy of Q plus Q minus 1 for each circle we have. So here are 3 circles, we have a 3, here we have 2, 1, and 2, okay, and so on. Then we just do the sum by columns, and then we take the alternate sum. We take the alternate sum, so we satisfy this minus that appears here. And basically that way we compute the polynomial. Maybe I lied a bit because there appears this term right here, but That's because right here it's k minus 1, and here we are just doing k. So that's just an adjustment. But we want to put k here because for the construction of the Khovanov homology, it's useful. Okay, so we just compute the bracket polynomial, and they just multiply by this term right here. So this diagram has all crossings negative. Okay, however you orientate it, you can check it. If you put this orientation right here or the other one, all crossings are negative. So you have p equals 0 and n equals 3. You plug that in, you compute, and you get the Jones polynomial. Okay, perfect. And you can also do that for the annular bit. Okay, but we'll see what we do with the Khovanov homology. Okay, we have to remember this cube right here. Okay, and right now what we define is a graded vector space that is generated by b plus and b minus, which carry a degree +1 and -1. So if we compute the graded dimension of the space, it's just q plus q minus 1. Maybe this don't tell us anything right now, but we can take the tensor product of k copies of p, and then we do a shifting of the degree. This is just notation, which this basically means that you take every generator which has some degree, and you change that degree adding r. Okay, so for example, if we have something like v2, we have a generator v plus with degree 1. So in this space, the degree of v1 is going to be 3, and the degree of v minus is 1. Okay, we just add r to this degree. Why is that? Because if we now compute the dimension of this space, we said that this shifting in degree, basically what it does is multiply the dimension of every generator by q. So we get this q to the r, and for each copy of v, its dimension is q plus q minus 1. So we get something like this. And this is quite similar to what we had before, right? They are just those polynomials that appear here. So that's what we are going to do. Instead of I'm going back right now. Instead of decoring each vertex by this polynomial, we put those that product of vector spaces. And instead of doing a regular sum, we do a direct sum. And that sum is what will be our chain groups. Okay, this will be our chain groups. And now we only need to give some differentials right here that join these two, and these two. Okay, this is what appears here. We define the differential just taking the direct sum. And remember that to compute the Jones polynomial, we had something extra. We had something like this. So to get this power of q, we just do a degree shift, this right here. And to get this minus, it's this shifting right here in these brackets. That's basically what it does is it moves all your groups to the left or to the right according to what it says inside. Okay? This is just moving the groups, but it won't affect the homology later, just where it's placed. Okay, so we had something like this, and now we have to do. Now we have to define the differential. How we do it? So if you notice, all vertices that are joined by an edge, the Kauffman states differ exactly on one smoothing. So for example, we have 0, 0, 0 and 1, 0, 0. They differ in the first crossing. So there is two circles that merge into one like this, these two circles merge into one. Or the other case that we can have is that one circle, like this one, splits into two. Okay, so we can define two maps that do precisely that, and we have explicit maps. So for each generator of the tensor product, we have its image, and for each generator of V, we have its image in the tensor product. So you can actually compute this. This is not difficult to do. And then what we will do is decorate each edge with one of those maps and take the sum. So we are facing with something like this. For each edge, we have a map, and then we just sum these three to get our differential on level 0. Okay. There's some trick because if you don't do anything else, the whole cube will commute. That's good, but you want the cube to be anti-commutative. Otherwise, you won't have that this is a differential. So you just have to change some signs over there. Just know that there's a canonical way to do this. And whenever you do this sum with some signs, you get a differential. Okay, this is marked right here with some bullets on the end of the differential. Okay, so this differential right here will have a minus, this one 2, and this 2 also. And well, so this is actually a chain complex. If we have a chain complex, remember we have that the image of each map is contained in the kernel of the next one. So you can do the quotient. That's the homology, and the homology of the chain complex is the Khovanov homology, just like that. It actually is a linked invariant, not the complex itself, but when you do the quotients, you get an invariant. Okay, and a good thing about this invariant is that it can recover the Jones polynomial. Okay, there's this thing that is the graded Poincare polynomial, which is just the dimension of the homology with some variable t, and when you take t equal -1, you get the Jones polynomial, or a version of it. Okay. Wait. Okay. If we did the Khovanov homology of the polynomial that we computed before, we would get this table right here. Okay, so this is telling us that on degree 0, this one is the homological degree. So we would have something like homology of this is on degree 0 we have z squared, then on degree -2 we have z plus z2, and z this is if I is 0, if I is -2, and if I is -3, and you get 0 in all other cases. But you can actually put it inside a table, because here you are only taking into account 1 degree, but the Khovanov homologies, it's actually bi-graded, so you have 2 degrees, because all the generators are a degree itself. So you can actually split this homology into its degrees. Okay, so you get this H I J. Okay. So this is the homology of the polynomial, and doing the thing we saw before, you can recover the Jones polynomial, and if you check it, you see that it works. So that's nice. This is the classical case. What what do we do with the annular Khovanov homology? It's the same, but before we only had one type of circle, trivial circles. Right now we have both trivial and essential circles. So instead of just assigning a vector space V to each circle, we will assign a space V for the trivial ones and a space W for the essential circles. And now we have another extra grade. So the annular Khovanov homology will have three degrees. The homological one, the J that appears here, which we call quantum, because it's cool, I guess, and an annular one, that is the one that spawns from these essential circles. Okay, so we have just both degrees. Okay, we have the quantum degree, the annular degree. We define those degrees for all these generators, and we assign a copy of V to each trivial circle as before, but a copy of W to the essential circle. Okay, and we do exactly the same. I shift in degrees, and we just do the direct sum. We get a chain complex. We also do this adjustment right here, and you do the quotient. Okay, but it's important to know that right now we have more than one option. Okay, before we only had two circles that merge into one, or one circle that split into two, but that's only one case. We can also have a trivial and an essential circle that merge into an essential circle, or two essential circles, sorry, that merge into a trivial one. Okay, those are the three cases that there are. There are more, you can check it. And we also have the counterparts for the splitting. Okay, it's just the opposite direction. You can define both maps M and delta for these cases. You do it exactly the same. So for each generator, you have the image. So you explicitly have those maps. So you can compute also the kernels and the images, and you can do the code. Okay, and we get that those quotients are the Khovanov homology and are also a link invariant, or an annular link invariant. And also, like before, if your link is inside a ball, then both homologies coincide. And to show some interesting facts about the Khovanov homology, we see that these two nodes that are called 5,1 and 10,132 have the same Jones polynomial right here, but their homology is quite different, right? We see that right here there are a lot more groups than on the left, but when you recover the Jones polynomial, those grade groups will kind of cancel out each other. So you get the same polynomial, the same Jones polynomial. Okay, so there are nodes that the Khovanov homology can distinguish, but the Jones polynomial doesn't. Okay, so it's a better invariant, but it's not complete. There are some nodes like these two right here that they are almost the same, but right here in the bottom it's kind of flipped, right? So they are not equivalent. You can check it with other invariants. I think the genius of the node worked, but they have the same Khovanov homology, so it's not the perfect invariant. And another cool fact about the Khovanov homology is that it detects the trivial node. So if you compute the Khovanov homology of a node, and it's the same one as the trivial node, then both your original node is the trivial node. This is not proven for the Jones polynomial. So we don't know yet if the Jones polynomial also detects the trivial node. Okay. I have prepared an example of annular Khovanov homology, but we don't have a lot of time left, so I think I'm going to skip it. But I want to make you understand that the Khovanov homology is computable. So you can you can have something like something like this, right? This is the hop link. Okay, so if we are in the annular case, we have to choose where the removed point is. So we can choose something like this. Then this is just the classical case, or we can choose something like this or like this. Okay, they are all different nodes or links, and you can compute something like this. So you will have, if I remember correctly, you will have something like this. Well, I'll put it here. So this is the 0, 0 smoothing, and over here you get something like this, and okay, well, this drawing right there is a bit bad, but whatever. So you can assign a vector space to this. So this would be something like B tensor W, because this one is trivial, this one is not. Here we would have an essential circle, same over here, and this is trivial and essential. So we will have something like this, and you just do the direct sum, and here you have the differential, and you can compute them. Okay, so you will get something like a matrix that looks something, I don't know, something like zeros and maybe some ones over there, right? This is not true, okay? But you can get something like this. So you can compute the kernel of this will be the two last generators. The image will be the first two generators of the other space. You can do the quotients and everything works, okay? Sorry. Okay. And to wrap this up, what it wasn't on purpose, I promise. I wanted to introduce two conjectures. Okay, so we work with the thickened annulus, but we can see this just as a torus that is solid. Okay, it's the same. An annular link is a link inside here or inside a solid torus. And we define the wrapping number of a link as the minimal intersection of this link with a meridional disk on the solid torus. Okay, so you can deform the node however you want with isotopies, with randomized moves, and you can move the meridional disk around the torus. You count the number of intersections you have, but the minimal number is the wrapping number. Okay, so it kind of tells how many times it winds around the center. And the conjectures that are yet open problems tell us that this wrapping number is precisely the maximum degree of both the Jones polynomial, the annular Jones polynomial, and the annular Khovanov homology. So when you have a Jones polynomial, you will have, I don't know, something like h times q plus h3 q squared, whatever. Okay, so you find the higher degree on h, it tells you that this degree right here should be the same as the raw union. Okay, and the same with the Khovanov homology. And well, just to end on the couple minutes that I have left, we could ask ourselves what's the next step, right? So we started with a polynomial, and then maybe right now it's a bit more intuitive, but some time ago it wasn't that clear that you could find some homology that could recover your polynomial, right? Because to any homology, you can do that kind of thing to recover a polynomial. So it turned to be true. Now you know that if you have an a topological space, you can compute its homology, right? So you can do something like what's the homology of the sphere, right? We have set or 0. So we can ask ourselves, is there a way to assign to each node or to each diagram a topological space such that its homology is the Khovanov homology? And the answer is yes. That's the Khovanov spectrum. If you know what spectra is, cool. If you don't, for us, for the purpose of this talk, it's just a topological space. Okay, so you just build somehow a topological space that's an invariant, meaning that if you have two equivalent nodes or links, the construction you do, these topological space are equal, right, to some notion of equivalence. So you can do that, and there's also a version of it for the annular case. Okay, so you can also compute a topological space or a spectrum for annular links. And what we are currently working on, my supervisors and I, is in a different construction that yields the same spectrum, but it's kind of easier to compute. And yeah, that's everything I wanted to tell you today. These are some references in case you're interested. Thank you very much.